This conference will now be recorded.
Okay. So in the last class, we have been kind of focused, or we were focusing on understanding the concept of stationarity. And to understand this concept of stationarity, we had looked into different methods and different tests. And one of the most important tests that we looked at was the Augmented Dickey Fuller test. Also, we had looked into the autocorrelation functions and the partial autocorrelation function as measures to identify, so rather autocorrelation function plots, ACF plots to identify stationarity, right? So over here we kind of had three measures on which we had focused. The first was the DF test, or the Dickey Fuller test, for an AR1 process, for a one lag process. Then we had looked into the ADF, which was the Augmented Dickey Fuller test. And the third that we had looked into was the ACF test. Right. So these are the three things that we had looked into. Right. Now, what was the importance of this, or what was the distinguishing factor of the ADF test? Why was the ADF test? Why is it that the ADF test is so popular over here? So let us kind of try to look into the reason, right? So let's have a quick look into the target variable or the dependent variable of the Augmented Dickey Fuller test. So one thing that we could clearly see is that the Dickey Fuller test does not assess whether YT is stationary or not. So what it looks into is that whether the delta YT is more or less constant or not. So are the changes between two consecutive lags very different? So is it that let's say the historical differences having a very important implication on the most recent leg, or on the most recent developments? So over here we have delta YT, right? So when I talk about delta YT is A0. This was the intercept that we had talked about. Plus we had talked about the gamma YT minus 1, plus summation I equals to 2 to P P beta I delta YT minus I plus 1. Right. So now where gamma is Y minus summation, and minus summation j1 to p aj. Now, how did we interpret this equation? So one of the things that we said is that if I had a one lag model, so if my time series was something like this, let's say yt equals to a0 plus a1 yt minus 1. So what would I do? So what I would essentially do is I would say that so yt minus yt minus 1 will be equal to a0. Yeah. So as I was saying, right, that now over here a0. Now if I am subtracting this, it will be something like this. Will be minus a1 yt minus 1. Right. So this will over here become a0 plus gamma yt minus 1. So where this will be something like 1 minus yt minus 1. So where gamma now is 1 minus a1. So over here, when I'm trying to test, so what will be the test that I'm trying to do over here? So one of the tests that I'll try to do over here is whether gamma is equal to 0 versus whether it is not equal to 0. Versus the alternate hypothesis that it is not equal to 0. Now, if gamma is not equal to 0, so if the null hypothesis is accepted, that gamma is equal to 0 is accepted, what it would mean is that the time series that E1 is very close to 1, or it is statistically significantly, it is not very different from 1. Hence, what would happen is that the time series is non-stationary, so which was typically the case for a random walk model, right? Now, on the other hand, the one thing that you need to do over here is you need to understand that yes, this is kind of not really the case if you see a multiple lags. So in that case, it is not only whether this. So then in that case, if there are two lags, then it should be that each of the row i's must be less than 1, which would imply such that their summation should also be less than 1. So it would mean is that the sum of the roots does not exceed 1, it is less than 1, and hence the time series is not, it's stationary, it's not non-stationary. But when you have multiple lags, along with this, there should be another criteria that the differences between the two lags, the coefficient corresponding or the sum of the coefficients corresponding to the differences of the historical lags should also be very close to 0. So what it means is, what it would essentially mean is that that uh, neither, so what it means is that neither the historical lags which are very far away should neither be impact, neither those historical lags nor the differences between the historical lag, the changes between two historical lags should not be impacting YT today. So what? So let's say I'm trying to see a stationary time series, right? So if there is an element of seasonality, right? Suddenly, let's say correlation with a lag which is 12 months back is very high with today's value of YT, then there is a certain correlation with that historical path. So it means that there are certain temporary factors which are impacting the prediction today, which should not be there. Whatever prediction for a time series is done must be based on the permanent or the long run behavior of the data, right? So this is where we would try to, so this is where we would need to contribute. So this is where the ADF test is used. So one of the things that we saw reconciling with this entire idea was the concept of the autocorrelation functions, the ACF. So over there we saw that this is 0, this is the full negative correlation, this is the full positive correlation. So the lag with the 0 lag, the correlation is full. Now if you go back 1 lag, the correlation for a stationary time it should be high but not fully 1. With a second lag, so as you are moving back in time or back in history, the impact of the historical fluctuations are growing lower and lower over here, right? So like this, so if for a stationary time series, you will see that this or ACF is a declining function. So it gradually declines. However, however, uh, the fall that we get to see over here is that, so one thing that we see with the correlation with the present lag of the historical lag gradually decline as you move towards the station. So if a time series is stationary, now let's say that, now let's say I increase this, right? So 6 lags back, I suddenly see this rising. 7, 8, 9, 10, 11, 12. So over here, one thing that you see is that the lag which was here and the height of this 12th lag is more or less similar. So it means that now one thing that you see is that this does not permanently remain high. So this is a temporary factor which is impacting YT, right? Which is as high as YT minus 1. So it means that every 12 months back, right? So every 12 months back, this is something which is like, you know, so every 12 months back, there is a problem. So, so there is a lag 12 months back, which is impacting YT today. But that impact is not a very steady impact. It's a temporary impact. That is why you see that it is falling, then rising, then falling, then rising. So there is nothing permanent or there is nothing steady about this correlation pattern, showing that this part of the data is characterized by something which is not stationary, which is something temporary in nature, right? But the relationship over here in this first part of the data is a very steady relationship of the or AC or the correlation with the lags, right? So in what it means is that on the whole data, right? So on the whole data, there is something which has happened, right? So on the whole data, that the time series is non-stationary, but it it has a stationary subpart and a non-stationary subpart. So it may be that because of the existence of this seasonality, right? It is because of this seasonality. Uh, so it is because of this seasonality of this association with this 12-month lag that the overall time series is becoming non-stationary. But one thing we can see is that clearly there are two kind of subparts to this. Right. So from here, the next thing that we need to understand is that on the whole data. So so this this shows that with the existence of seasonality, uh, there is some issues with this overall data, right? So there exists seasonality or some temporary components which creates this fluctuation, right? So 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 if you look over the entire span of the data, so your gamma will test towards 100. So over there, the row had so this part will dominate the overall distribution of the rows, right? And from there you will see, or from there what we can see that yes, the overall data becomes non-stationary. So so this later part of these older lags will dominate the impact of these earlier lags, and on the whole, the data will be a non-stationary data, right? Now, now here comes the last trick. So this is how you can interpret the existence of temporary factors in the data. Now, this is a very big advantage of the ADF test in describing the non-stationarity, as well as this is also a limitation of the ADF test. Right. Now, one of the biggest advantage of the ADF test is it considers the entire distribution over all the time point, the entire data, in deciding whether it is stationary or non-stationary. At the same time, this also turns out to be the limitation of the ADF test, right? Of this ADF model. Okay. Now, one of the important questions that come out over here is that why am I saying that that considering the entire data, fitting the test over the entire data series is an advantage as well as a limitation of time series models. Why am I saying? So let's look into this. So over here, so let us consider a situation something like this. So when is it that the ADF test is a successful test and can be applied, and when is it that ADF test has a limitation? And the next question that comes out is how do we avoid that limitation? How do we deal with that limitation? The ADF test. So this is the advantage. So when is it that using the ADF test is an advantage? Okay. So let us consider this trend. So let's say this is the origin, this is the time, and I have the YT series over here. So let's say my time series is something like this. Right. So now if I try to apply ADF test, right? So the question is that does this ADF test, does this time series or testing this time series with an ADF test and getting a non-stationary time series, so is this a proper test, a proper thing to do? So let me just draw a constant mean, right? Now, if I plot the variance, if I capture the variance, the deviation from the mean over here, I will get a typical, I'll get a typical variance. If I do it over here, I'll get another typical variance. If I do it over here, I'll get a typical variance. If I do it over here, I'll get another value. If I do it over here, I'll get another increasing value. So one thing that you can see is that there is a trend in the variance, right? And the variance is increasing continuously over time. There is a trend in variance. So what it means is that across multiple subsamples, what you will see is that the difference, I mean, the variance keeps on increasing, and hence the time series is a non-stationary time series because the variance is not constant, so it is non-stationary in variance. Non-stationary in variance. Non-stationary in variance. Okay, in questions up to this point of discussion. Yes, Padmini, you can put your question on the chat box. Okay, so I'll take that question up. That in case we run the ADF test, what typical values can we expect as outcomes? I'll come to that question very soon. I'll just come to this question. Okay. Okay. So over here, so just let me finish discussing this advantage and disadvantage of the ADF test. Then we'll just come to it. Okay. So over here, now if I, in this kind of a time series, if I use the ADF test, right, then it is correct to use the ADF test. And the ADF test will give me a appropriate result. So it's a correct application of the ADF test. The ADF. Because this series is a pretty continuous series and you can see this trend changing gradually over a period of time. So things have been, so the variance has been unstable over a period of time and hence you can use this ADF test. Now the question that comes out is, when is it that it is wrong to use the ADF test? So the next question that comes out over here is the ADF test disadvantage. Disadvantage. So let us see. Okay. So let's say I have a time series which looks something like this. Right. So one thing that we can see is that there has been a sudden change or there exists a structural break at one given point. So on the right hand side of the structural break and on the left hand side of the structural break, the time series is more or less stationary. But if I consider the whole data, right? Now, if I consider the whole data and I get a straight line mean, then there is, so that is where, I get to see that this is not something. So then on the whole, the stationary test will give me a non-stationarity in mean or variance, and it will give the result will be a non-stationary will that be of non-stationarity. However, in these two subsets, so this is a stationary subset. this is a stationary subset. So this is a stationary subset, and so is this part a stationary subset as well. The only point is, or the only point of non-stationarity is this break. Now, given that there is a break, so on if you apply the ADF test on the whole data, the ADF test will give you a misleading result, right? So over here, it is an incorrect application of it is an incorrect application of the ADF test. Correct application of the ADF test. Right. So while ADF test is a very widely used test, so the existence of structural breaks in the data is something that needs to be taken care of. Now the question is that what is the type of output that I will get? So over here, so ADF test is a test. So once you run the test, so you will get the for that delta for that gamma, you will get the value of the augmented Dickey Fuller test statistic. You will get uh, the p-values, and given the level of significance, we will have to decide whether it is stationary or not, right? So it will report the different measures of the test statistic. So the equation over here is the delta y is the ADF equation. The gamma that I get is the test statistic which is to be tested, and this gamma is obtained using OLS estimation. And given that the OLS estimation is performed, you will get a value of the gamma, and you will get a value of the p-value, you will get a value of the degree of freedom, and given the level of significance, we have to decide whether that p-value is, so whether that gamma is significantly different from 0 or not, right? So let's say, so that test, so how will this test then look like? So this test will be H naught gamma equal to 0 versus the alternate hypothesis gamma not equal to 0, right? So this is what the test hypothesis is. Now with this test hypothesis, you have the test statistic which needs to be created. Now obviously the test statistic over here will be the augmented ADF test statistic. The ADF test statistic is something like this. So it will be gamma hat minus expected value of gamma hat divided by the standard error of gamma hat. Okay. Now, when I'm looking into this ADF test, right? Now the question that comes out is that how do you estimate, or how is gamma hat estimated? So you estimate gamma hat using OLS. Now under OLS, we know that from our discussion on the linear regression model, we know that the parameter estimates are nothing but blue, right? Now for a detailed discussion on uh, for a detailed discussion on linear regression, so we already have our sessions, but in case you want to look up, so for this linear regression, I have in my YouTube channel, I have a playlist over there which is solely on linear regression, right? So you can go and take a look over there as well. So I'll share the link with you. I had uploaded all the video recordings over there. So if you go to this particular playlist, which is the predictive modeling techniques, so you have all the video sessions for linear regression explained over here. So I'll just put that link over here. Okay. So we have the blue estimates, right? Now once we have estimated the blue, so obviously this expected value of gamma hat should be equal to gamma, because it is unbiased. Now, and if an estimator is unbiased, we know that the expected value is equal to the parameter. The expected value of the estimate is equal to the parameter. So it is gamma hat minus gamma divided by the standard error of gamma. Now, what I want to test over here is that whether gamma hat is different from zero or not. So under the null hypothesis, under the null hypothesis, yeah. So under the null hypothesis, gamma is zero. So your test statistic automatically becomes gamma hat divided by the standard error of gamma hat. Okay. Now under the null hypothesis, so this is what your test statistic becomes. Okay. Now having seen this, the next question that comes out is how do I, or what the test results will be. So to do this, so corresponding to this test statistic, there will be a p-value which is generated. If the p-value is less than the level of significance alpha, which is by default, which is mostly 0.05, which is 0.05, right? So if the p-value is less than 0.05, then the H naught is rejected at alpha level of significance. Is rejected. Now, if you are rejecting H naught, what it essentially means is that your time series is stationary. Is stationary. Okay. So A0 is rejected and time series stationary. So if your null hypothesis is accepted, what it means is that the sum of your roots is something which is statistically insignificantly not different from one, and hence your time series is non-stationary. So how would the result look like typically? So you will have the test ADF, ADF stat value, you will have the degree of freedom, right? You will have the p-value, and you will have the name of the variable. Name, ADF test, the degrees of freedom, and the p-value which is generated for each of the variables is something that we will have in our right. So this is how your typical output would be, and this is what you are expected to do in the ADF test. So does that answer your question, Padmini? Okay, perfect. Okay, fine. Okay, okay. Okay. So now the question is that this is how you do the conventional Dickey Fuller test, the augmented Dickey Fuller test. Now the question that comes out over here is that if I have a structural break in this situation, how do I identify or how do I do the ADF test? Because if I have to test for the stationarity of the time series, it has to be the so it has to be your ADF test, right? Now, if you are actually, so if you have a series which has a structural break, so let's say I have a stock market time series starting from 1900 till the last year or this year, let's say last month of this year. So now there has been several events which could have created a structural break. So one such point was the 1991 opening up of the economy and you had the reforms and everything. The second shock may have come around uh, the global financial crisis. The Then you had GST implementation, then you had demonetization. So there has been multiple events which has always caused the stock market's behavior to change, and there were certain structural changes which have changed the pattern of the stock markets forever. So now, what exactly then is a structural break? So structural break is a break which permanently changes the overall trend of the stock of the time series variable. So if you have, let's say, I have a situation like this. Uh, so let's say I have a situation like this where I'm looking into the stock market behavior before 1991 and after 1991 post liberalization. You will see that the overall trend of the overall trend in the markets has totally changed. Now, after so when there was a change in the let's say in the growth strategies and everything, and the economy was and the world economy was booming, so there a change in the trend had happened, and then again after global financial crisis the markets had crashed back, and then it needed sometimes to come back. Now if a trend or if a shock or a change has totally changed that trend, right? So that or there has been abnormal periods, let's say there has been a war, there has been a so there has been a war or there has been major policy changes, then which impacts the time series forever and causes its trend to change. So those events are something which has totally changed the trend of the time series variable. Then you say that that's a structural break. So structural break, it should be a break which permanently has changed the long run trend of the time series, right? Now if that returns back after, let's say, 2 3 periods or 4 5 periods, then that was not a structural break. So that structural, that break or that time point must have, or the events at that time point must have impacted the long run behavior of the time series. Only then that's a permanent irreversible trend, right? So in such a case, so if there has been a check like that, then I cannot use the data before that structural break has happened, right? So we need to understand first of all that how is it that structural breaks can be used, or how is it that structural breaks can be studied. So if you have events, let's say you are trying to assess or analyze the stock market behavior, the sensitive behavior in the neighborhood of the global financial crisis, so your data is let's say from 2005 till 2015, or say yeah, it's from 2005 till 2019, then what you are having is a 2008 period in between. So you know that if that event is there, then it may totally cause a shock in the, or may can make the data series the ADF non-stationary. So the ADF can give you non-stationarity, but on the left hand side and right hand side the behavior was pretty uniform. Then that part can be a potential structural break, and that is what we need to understand. So there is a statistical test to do that. So there is a test called the chow test. The chow test, which can help you capture the structural break, right? So we'll come to this test a little later. Now another way of doing so a more uh, so a better and a more robust way of doing this is the rolling sample test. The rolling sample test. So how do I do the rolling sample? What I do is I create certain subsamples in the data. Right. So what we do is we create certain subsamples in the overall data. And for each of these subsamples, we compute the ADF series. And then we plot the distribution of the ADF series. Now, after we plot the ADF series, right, the ADF test statistic series, and if we find that there is an abnormal spike at a point of time, and then the spike again dies down, right? So if there are no structural breaks and the data is non-stationary, then every time the ADF series must be lying, or the ADF values must be lying in a given interval, or must be very symmetrically distributed over the subsamples. But if for a specific sample, if for a specific sample or one or two samples around a given time, right, you see that the ADF series has triggered out of the or the other surrounding values, then what you can do is that so then what you can essentially do is you can say that okay, look, this is what is here. So this is at this point the ADF series has triggered a red or has triggered off from the overall distribution. I can see an unnecessary spike in the ADF distribution, and therefore this point is a potential break, right? So the ADF values after that break, right, should switch over back to more or less similar ranges once again. So if you can see that more or less it is stationary at, so before that point, stationary after that point for all the subsamples, then at that particular subsample or at that point, there is considered to be a structural break, right? So what I'm trying to say is, let's say I have data points like sample points 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Right. So now I'm trying to create subsamples of say size 3. So 1, 2, and 3. This is the first subsample. And I calculate the ADF of this, which is ADF 1. The next point that I calculate is, or the sample that I create is 2, 3, 4. ADF 2. Then the next point over here will be 3, 4, and 5. So from there I'll get ADF 3. Right. So you can see that we are actually getting a distribution of ADFs, right? So I'm getting an ADF distribution. Now, if there is, so if I plot that distribution and I try to check whether there is an unnatural spike in that distribution, then we can say that yes, this series, then we can say that at that time point, the there is a structural break. So if you apply the ADF test at that point of time, you will see that this time shoots up, right? The ADF shoots up at that point and then again dies out. So, but if you use it on the whole data, right, that data will always turn out to be, it will always turn out to be non-stationary. Whereas if there's a structural break and you leave out the data before the structural break and consider the series after that, then this problem may get resolved, or the extent of non-stationarity may go down, and then you may need to solve for these. Right? Okay, can you hear me now? Okay, so in case you cannot hear Padmini, what I'll suggest is you drop off and join back, right? And then we can take it up from there.
This conference will now be recorded.
Okay, so over here we have seen how the rodent sample test can help us solve this problem of to overcome the limitation of uh, how has it helped us overcome the limitation associated with the ADF test. Now, one of the important, so a few important questions that Okay, so over here, so one of the things that we have seen over here is that we have the ADF test, right? So we have the ADF and we have so the limitations of the ADF test and how is it that the rolling sample test can uh, help us solve this problem. So now with this, we have covered mostly the parts associated with stationarity, testing the stationarity of a time series, challenges that you can face, and so on. And this is the first step of any time series model development and is known as the identification step. So the objective of this step is to identify whether a time series is stationary or not. And if it is found to be non-stationary, then the next question that comes around is to treat this issue of non-stationarity. Right. So the two broad processes which are used to test for non-stationarity are the is the difference stationarization and the trend stationarization. Right. Okay. So we will be so the next step that we take is we discuss this issue of stationarizing. So how is it that we would stationarize a time series, right? So we'll take that discussion up from the next class. So we'll discuss how to stationarize, and from there we'll move on to the estimation of the time series components, the AR component and the MA component separately from tomorrow's discussion. So let's take a pause here for the day and let's review tomorrow again at 9 a.m. Thank you.